Yes. Okay, good afternoon, everyone. Thank you for making it to this TSVP seminar today. It's my pleasure and honor to introduce Dr. Keiko Aoki, who is she's a visitor under the TSVP Domestic Visitors Program, and she's collaborating with my group. And starting from February, she will also be part of our group full-time. So Dr. Aoki received bachelor's, master's, and PhD, all three from Keio University. And the remarkable thing is she has spent most of her career in an industry while continuing to publish papers. So it says something about what we are not getting right here. So we have a lot to learn. Today, she is going to talk about the spontaneous formation of soft matter. So without further ado, and please feel free to ask questions at any time. Thanks.
So thank you very much. First of all, I would like to thank the TSVP for hosting me, not hosting me beautifully, not only in academic perspective, but many different ways. So I first want to thank you. And thank you for coming, all of you. So today's my talk is about spontaneous formation of soft matter. Basically, I am a condensed matter physicist using the computer. So today, the tool of research is about, well, computer simulation. And specifically, it's about molecular dynamics simulation called stress control method. And today I would like to talk about three systems, different systems. One, liquid crystals, which I have been doing. My PhD thesis was about liquid crystals, so I'm doing it all through my research career. And the second topic is soft matter crystal, which appears just below the liquid crystal phases. And the third topic is liquid-liquid transformation, which appears completely in a different system with only isotropic interaction. So today is a general audience talk. So I will start from what is computer simulation, what is molecular dynamics simulation. So molecular dynamics simulation is basically calculating the dynamics of a whole bunch of molecules all at once. So for instance, if you have a Hamilton equation of motion, we have position and velocity at the same time. We solve everything simultaneously. So in the case of the simplest Hamiltonian, we calculate the position from the velocity. We calculate the velocity from the force exerted to it by the surrounding molecules. So the interaction comes in here. So this is the reason we have to do all the molecules all at once, since all the molecules are affecting each other in a very crowded, it's basically I'm doing condensed matter, so it's in a very crowded environment. So, but how do we implement equations on computer? It's the next question. Of course, we have to discretize it. In a sense, for instance, if we have a continuous time evolution, we have to cut it piecewise, cutting the time evolution piecewise. So we have to do it, but we have to do it very carefully here to preserve the structure of the equations. So imagine that we have this black line is the true solution of the equations. And then if we do it correctly, the discretized solution will be something like this orange dotted line. So basically, we have a sort of tube which contains both the true solution and the calculated solution. So if the precision is not so good, we might have, well, the tube, which contains the both solutions, might be very wide. And then we might, lose some fine structure here. But basically, even if the precision is not so good, if it will stay in the same tube for a very, very long time. So that's the power of geometric integrators. So not only the equations are important, but how you implement it is very, very important. So what is stress control method? Stress control method is one method of molecular dynamics simulation, which the volume and shape of the simulation box, which contains all the molecules, will coordinate with all the dynamics inside it. So this means that, well, you can maintain hydrostatic pressure, or in some cases, constant surface tension, even under non-equilibrium relaxation. So how we solve it is we implement it to an explicit integrator, which of course guarantee the calculated solutions will not deviate from the true ones. So the geometric integrator. And so this type of thing is the difference with conventional methods is mainly that since we can do a hydrostatic pressure evolution under non-equilibrium relaxation, this means that we can treat self-organization or spontaneous appearance or disappearance of the surface. So I just want to remind you what stress tensor was, or pressure tensor. I prefer to call it pressure tensor, but the diagonal elements of this pressure tensor is, of course, the same in each direction when we are under hydrostatic pressure. When we have surface tension, if the surface is along the XY plane, we have an anisotropy like this in the diagonal elements of the surface tension. So microscopic values of the stress tensor reflects the dynamic state of the molecules inside it. Now, well, there are several different versions of this stress control method, which these blue values show externally given values. So the PEX is external pressure you want to keep the system in. And this is, for instance, normal pressure in the normal to the surface. And the surface tension gamma is also external given value. So the difference is that not only the ensemble average is guaranteed to fluctuate around the externally given values, but during the time evolution, it will have some relationship like these, which basically guarantee it's hydrostatic or it is evolving under surface tension. Or you can do it with constant volume, just changing the shape, that it will have some relations to maintain hydrostatic pressure. So today's talk is only contains the results obtained by this constant pressure methods. So I have talked about what kind of tool of research I use. I didn't go in detail, but today is a general audience talk, but it's a method that guarantees some property during the time evolution. So the first system I would like to talk about is the liquid crystals. This is in collaboration with 3 chemists who actually, I will show you later on that, who synthesized a series of liquid crystal material and did a lot of experiments on it. So what is liquid crystals? Basically, it's a liquid with orientational order. But since it's a liquid, it can flow. You need a container to keep the shape of the material. But since the orientation is on average in some direction, you have anisotropy. You have anisotropy and optical or electrical or whatsoever. And it's usually not really elastic. Maybe might be elastic in one direction, but basically it's the elasticity is not the true strong elasticity, it's viscoelastic. So if we measure some things in liquid crystal phases, like refractive English, dielectric constancy, viscosity, electric constancy, we have anisotropy depending on the direction. Well, if you have a shape which is anisotropic, you will get liquid crystal phases. But here I would like to, for instance, disc-like or bowl-like liquid crystal exists. But today I would like to concentrate on the rod-like molecules. So the simplest liquid crystal has only orientational order like this. It's the nematic liquid crystals. You probably have in your liquid crystal displays are nematics with a little bit of chiral dopant, and then which makes it easier to, the molecules to shift directions inside your display. So this is usually used. And of course, because it doesn't have any extra order, the viscosity is the lowest usually. But there are other types of liquid crystal called with a loose layer structure. It's very loose. It's not really, still usually molecules can diffuse between these layers. But well, if you look, well, but still you get some definite layer length in, for instance, X-ray diffraction patterns, or so it has a characteristic length scale. So these are called smectic liquid crystals. It's if you put it on a substrate, it will be flat interface. But these interfaces are so loose, you can have a curved interface. So these curved interface, we have a lot of, well, I won't say it's really confirmed structure, but it's supposed to make some triply periodic minimal surfaces. When I say triply periodic, means that we have periodicity in 3 directions. So in a sense, it's we have 3 orthogonal directions, symmetry. So we call it cubic phase. Not necessarily in a sense of a crystal cubic lattice, but we have orthogonal 3 directions here. So there are different kind of liquid crystals which not the molecules itself make the structure, but the defects appearing in them make a structure. For instance, this double twist is, if you have a very strong chirality, you will get some kind of rod with, you have twist in this direction of the rod, and as well as in the diameter direction. So this is why it's called double twist. And you have some kind of double twist things. This will form a defect, of course, because it's very strong chirality. It can't really merge in a low energetical mean way, except to maintain these defects. So for instance, if the lines, these tubes line in a certain way, they are called, the defects line are reflecting optically. So we have a very beautiful blue. If you just look at the material, it's really shining in blue because of the selective reflection wavelengths we have. So yes, for instance, if we have the smectic liquid crystals, the loose layer structure I have talked, we might have defects as well. So we call it dislocations. Basically, these are line defects. For instance, this edge dislocation is, the line is normal to the screen. So we have a line defect. And in 1972, the Jan has predicted that if you have if you change the strength of the defect, you might get something with some kind of structure with the defect embedded in it. So if you have a screw like this, the layers can't really slowly twist, so it does twist discretely. So you have a defect plane in between those domains. So this is called twist grain boundary phase, which was discovered quite a long time ago, and it has been intensively studied. But in the case of, well, de Jong also predicted that if you have a bend or edge dislocation, you might have something as well. But this bend grain boundary phases was not discovered. But today's talk is that we have discovered this bend grain boundary phase by molecular dynamic simulation. So these are the chemical substance which my collaborators synthesized quite a long time ago. And the interesting thing is usually liquid crystals need this alkyl chains on the end. And you have to have a certain length to get the liquid crystal phases. So changing this length will change, of course, the phase diagram usually. There's something called odd-even effect. If you have odd values and even values, you have something like a zigzag in the properties. But here, we change the length here on both sides, and we change the temperature, and this is the phase diagram that they suggested by their experimental experiments. And here it's very interesting that they assume, they tried to calculate how many molecules there is in one lattice. And it's quite, small. But, and they say it's a cubic phase. You have a chiral cubic phase in the middle, and then changing the alkyl chain you have the same one on both sides. So if you, and they suggest from experiments that the alkyl chains are melted completely. So if you look at the chain volume and the core volume, you have something like 0.4 to 0.8, and the phase diagram will become like something like this. So the question, in the middle, we have quite a different, structure here, but still it's quite small, you can tackle this. You seem to be able to tackle this easily with molecular dynamic simulations. So
I have a question.
Yes.
I realize this is experimental data, not from the molecular dynamics, but do you know what they mean by second heating over there?
Oh, yes. Well, usually it's easy to get a hysteresis in such systems. So if there are
they do a breaking cycle and then
yes, so when, especially when going down, you might get different kind of liquid crystal phase, metastable liquid crystal phase. So they do it twice, and this, if it's much stable, then doing something once, So, and heating it is better, of course, because we don't get any super cooling. So this is why they have second. So where was I? So well, in these cases, the orientation is define the surface, and well, the X-ray diffraction predicted that it might be something like this. But of course, we don't know because in cubic phases, the usual, for instance, optical birefringence which appear but don't appear here because it's cubic. And so it's very difficult in a sense compared to other liquid crystals, which are quite easy to identify. So especially the question is, this is diffusing, really diffusing. So they know that the molecules are diffusing. But in such a complicated structure, how are the molecules diffusing is a thing they wanted to know. So they suggested to me that, well, in this system, hydrogen bonding is not important. And, well, soft core excluded volume is important. And the alkyl chain is completely melted. So they gave me something like this, which has a bulky head on both sides where the alkyl chain is melted. But well, I suggested let's start first with anything, just a Sophila cylinder, because if you have a rotation motion, it's like if you take the average excluded volume, it's like a tapered molecule. So that's where we started, agreed to start, and if the alkyl chain is really melted, it only acts like a solvent with the isotropic pressure. So I also use this, stop worrying about the alkyl chain, but I decided to change the isotropic pressure, which is exerted on the core. And so replace the effect of the alkyl chain length by external pressure, which is isotropic, hydrostatic. So I start with a very simple model, which has which interact between minimum distance, and here it's the length is 3. I have number 1,920 molecules, and I stacked it 8 layers in the beginning. So I'm using periodic boundary condition in all directions. So any kind of structure we get here is guaranteed to be triply periodic. So we don't have to worry about anything about the triply periodic stuff. And I use the stress control method during the time evolution. So what I get with I got some cubic, well, a phase with cubic symmetry, which 3 orthogonal directions. And then if I change the pressure at different temperatures, I have it. And if you look at the core volume versus the volume of the total volume, it is just like this chain volume. The percentage is, well, it looks, the core is against the, in this case, it's a void, but it's in a good ratio. So I look in details in the system. I will show you two different phases. One is when I kept this constant. They form, at the beginning, they drastically change the simulation box, but they're quite stable. And the other one is I change this temperature at this time, in between my time, and then this simulation box length suddenly at changes drastically. So it shows that something happened here. But the pressure in all directions, we see that of course, it's fluctuating because we are calculating all the total of the molecules, but still it's fairly good hydrostatic pressure on it. So I'm sorry, it's not. Can I click it? Oh yeah, so the colors are not good because my graphics is bad, but oh, it stopped. So, but and if you see it from the normal directions to the simulation box, you really don't get the structure. But if you just turn it around a little and find some place that you will get a clear structure, you can. It's of course I am writing in here. I'm writing the molecules very small because you can't see through the structures. But so this is. Seems to be fairly stable for a long time. And we, it's a structure like this. So, so basically this structure, I will call it phase A. There are two smectic structures. I call smectic structure a set of smectic layer parallel to each other. So this is a smectic structure on a different orientational smectic structure. So the smectic structure are normal to each other, but they have 45 degrees against the stacking plane. They have a stacking plane in between. And there are guide planes with half of this repetition of the structure or 1/4 of the repetition of the structure. But here we have to be careful because the smectic layers are continuing normal to this screen, and there's periodic boundary conditions. So we really don't have, we have two characteristic length scale, which is the layer distance between the smectic layers and this repetition of this structure, but we don't have the third characteristic length. So if you do it in a crystal way to analyze this, it will probably assume that we have a third characteristic length, which is the same to each one of these, but that will make the assumption totally wrong. We really don't know if there is a third characteristic length. And if you have a larger system, of course, these layers might curve. So we have to, use some kind of topological notation to identify these structures. So the topological notation but still we have a metric. So this topological notation with the metric, I chose to use the orbital notation. So this is characterized as a deglide to do cross the write it. And so basically, if you are looking into soft matter structures, you really have to be careful that you don't pick up a wrong assumption. And there's not a well-defined lattice like in crystals. So I go on. In this simulation, I slightly increased the temperature from what I got at the At the beginning, I increased the temperature. It stays a while in the same structure, but again, this is normal to the simulation box, but this is in a direction that you can see the layers well. So it spontaneously changed to a different structure, but still it has a cubic symmetry in a sense that we have 3 orthogonal directions. So the blue ones are in one direction, the symmetric structure in one direction, and the yellow one is in normal to that directions. So the only thing I'm changing is temperature.
Constant pressure for the volume adjusting so to maintain constant.
Yeah, yes. So it's constant. This has the same value externally given, same pressure value, but I changed the temperature. Of course, the pressure and will fluctuate because that is, you know, because of the molecules are moving around, then we have pressure. So, well, we have a clear phase transition here, spontaneous phase transition here. So, well, we can say we have a chiral axis which is discretized. You know, it's not a smooth screw, but it's discretized in 45 degrees. So if we look at the diffusion, the original one is the diffusion, which looks not so much, but if we look at it, it's still quite diffusing. The second one, where I increase the temperature, is quite diffusing a lot. Of course, it's diffusing in the XY direction, which is where the symmetric structures are easily diffused, because this diffuse and this diffusing along the symmetric layers is much easier for them. But still, we have a little bit of, you know, diffusion along this, yes. And if you look at this, this is a lateral orientation of the molecule. If you just trace some of them really changes, flips in a short time scale and goes, you know, to the different domain. So still we have completely different domains, but still we can, there are molecules are diffusing. So it's really a liquid crystalline phase, both of them. And this is a slightly different thing, but if we started from this cubic phase, we saw B phase like structure. This is, in this case, the green and pink is in the orientation is 90 degrees different. And if we, you know, the thermal fluctuation easily brings it back to the lamellar phase. In this case, you can see this is the simulation boxes in the real length. So you see a very slight change in the environment will be able to change it back to lamellar. So this is, you know, it is said, for instance, in cells, that you can easily go back and forth with some kind of structure in the lamellar phase. So it seems to be doing it here too. So we have seen new liquid crystal phase, which is made up of multiple symmetric structures separated by the plane of edge defects, because these are, you know, for instance, this is completely, the layers are cut off and look at different directions. So we have, well, we can call it end-grade boundary phase. And here we only could detect something that the symmetric structure align along or 45 degrees or like normal to the stacking plane. And molecular diffusion is fluid-like. And well, even molecule, the amount is smaller, but molecules diffuse among different symmetric structures. So this is the first part of my talk. Of course, so we go back to Dujan's prediction. It was, we have symmetric liquid crystal with edge dislocations, but it it transforms to an isotropic liquid. It's a first order transition above it. So this scenario wasn't correct for the bend situation, but the mathematicians argue that they are topologically different, so they don't, this prediction is not correct. So no, next talk is, I still have some time, soft matter crystals, which is what I call a soft matter crystal is something with a higher order structure made from soft matter material. What I call a higher order structure, I will go on to explain it in the next slide, but well, it's configurational structure built by primary structures. This I will explain to you later on. But in liquid crystals, there are lyotropic systems and thermotropic systems, which lyotropic systems have solvents. So they are, the transition is driven by concentration and temperature, but in thermotropic systems, which I just show you was a thermotropic system, is without solvents. So it's the phase transition is purely driven by temperature. So to explain what primary structures and higher order structures are, I use this lyotropic system because it's probably much easier to do so. So if you have some kind of amphiphysical self-assembly, they usually, if you have a concentration high enough, they will assembly in a missile. It will be a sphere missile or it will be a rod-like missile. So this assembly is the primary structures here. But these, spheres or rods can assemble in a, for instance, hexagonal way or a cubic way. So this higher order structure is made up from not directly from the molecules, but a structure which is formed by the molecules. So we go on to do a similar simulation, which I just showed you, but now the temperature has, I increased the molecular length. And so if we increase the molecular length, the temperature, transition temperature increases. So we use the same hydrostatic pressure method, but now we are doing a time evolution near the crystal liquid phase transition. So if we are close to the liquid phase transition, we are using this large fluctuation near the transition. So, so here we have but this is what I calculate, simulate. But since it's triply periodic, we just show you to copy them and show you which makes it much easier to recognize the structure. So here, if we have a layer spacing of D, this unit is 5D. We have a little bit of irregularity in this region, but basically they have all of them have the same length. But we also get something with two primary structures. In this case, we have 3 layers here. So this length between this red line and red line is 3 layers. But we also have some kind of, 4/3 plus the layer structure. So we have, of course, we have, if you look at the cell, it's not commensurate with the simulation cell. So you have to look at the direction and find this structure, but still it's triply periodic because it's under the periodic boundary conditions. So you can go on to find 3 primary structures. This is D, 2D, 3D. And everything, it starts from a stacked layers of the same thing, but you just form a kind of structure like this by thermal fluctuation. So we go on, and there's 3 primary structures here, but instead of an integer, we have, of course, here is an integer, but we have 3 lengths, and it seems that the 4/3 is always appear in some of these. Here we have 2D, 4D, and 4/3 again. So this is another 3 primary structure crystal. We have now 5D and 4D plus 4 and 6D plus. So, but we also can have curved surface in this type of crystals. So you have, this is, I'm showing you this and this in a slightly different direction. So here it doesn't seem like a crystal, but if you slightly change the direction, you can see it, it's clearly a crystal. So the axis of crystal is could not be seen in one plane, but it is a crystal. And you have in these, you can sustain the curves. It's just frozen down to a crystal. So this is another structure with curved surface. So we have something that which is not very clear, but looks like the other straight crystals. But if you just change looking at the direction, there sometimes you can see something like a minimal surface. So we have self-organization of soft matter crystals. We have some characteristic lengths with this 4/3. I will show you why this appears, but or integer. And well, we have longer characteristics lengths for higher pressure and temperature. So this is different. This is basically, this system will become a liquid crystal, but in between you could see clearly that there's a 1/4 structure here because of the fluctuation we have. So the things appearing in that crystal is directly affected by the liquid crystal phase we have above. And the fluctuation is just frozen in. So
there is curvature, there is energy associated. Somehow.
So it's the problem if the energy is lower to cut it off, or just, but for instance, if it's, this is soft, this is a liquid crystal phase with diffusion. So if you have diffusion, maybe the relationship of the energy relationship might change. But so at the beginning, maybe the BGV phase seemed to be very far away from the minimum periodic surfaces. But if you look at these type of surfaces and you cut it in different directions, this really looks like, some of them really looks like the BGV phase I get. So maybe we're not so far from, maybe they are not so far as a structure as it seems at the beginning, but I'm working on this, so I don't have a conclusion. But the third topic is about liquid-liquid transformation. This is completely a different way to use this hydrostatic pressure MD method, because now what we're doing is we only have soft spheres. We want to see the free energy landscape, how it looks like. And then to investigate it, we change the mass of the thermostat. The mass of the thermostat is something like a piston mass for the barostat. If you have a very heavy piston mass, or a light one, the light one will, will go to a static position easily than the heavier one. So we use that speed of response to the thermostat to get to these local minimas. And this is simply liquid, solid liquid transition here. We have a melting here. So it jumps quite significantly. It's a first order transition here. So we have crystals as this black dot, and we have a lot of amorphous solids on above it. But we also have a kind of peculiar, I will call it liquid, second liquid. So usually the liquid line is extrapolated to assist to what is called supercooled liquid. But well, we don't get it by supercooling. We get it by a constant temperature, constant pressure, time evolution, deterministic time evolution. So this is not thermally supercooled, but it's confirmed to be, there is a metastable state, energetically metastable state here. So this triangle, we will focus on this triangle, black triangle phase, which is the density is higher than other amorphous solids. But if you look, of course, if you can look at the potential energy. The potential energy shows that the crystal is much more different than the amorphous, but basically we have the same diagram. So this is diffusion constant. So if you compared it with the supercooled liquid, this is only 1 or 2 orders smaller than the supercooled liquid. So basically it's be called liquids, I think. But it has only limited temperature range. If you go, for instance, the highest temperature, the lowest temperature you can maintain this state is 11, this black one. And if you go to different temperatures, lower temperatures, you will get transformations, but it will occur discretely among discrete states. So if we look at the heat capacity, if anyone has seen a liquid transition heat capacity curve, it really looks like the experiments. And but the peculiar thing of this is that if we measure the elastic constants, this is, I write it with a bunch of other amorphous solids, but this black one with this color triangle is the focus here, and it suddenly drops after the density has got higher. And here it also drops here, and the strain ratio usually go up. So when it comes liquid, it goes to 0.5, but here it's going up after the transformation to a higher density. So it's softening at lower temperatures. So we used a stress control hydrostatic pressure method. The difference is that we may explore the free energy landscape by changing the mass of the thermoset. And usually a free energy landscape is temperature dependent. So this comes in where this method is good. Compared to supercooling, you have to change the temperature. You're going on and on with a different, the free energy landscape is also changing while you're changing the temperature. So it's very difficult to conduct a simulation like that, but you can do it with a different method. So here, the second liquid transfers to a supercooled liquid at high temperatures and to a softer state with high densities at low temperatures. So, it's just about time. So I talked about 3 examples of spontaneous formation in simulations. The dynamical evolution under hydrostatic pressure is the key to get these spontaneous formations. And I think it's not stressed enough that how important the system size is in molecular dynamics simulations, because of course, statistical physics teach you that if you have a smaller system, you have a larger fluctuation. So if you want to use the thermal fluctuation as a driving force of spontaneous formation, which nature is doing, so you better have a small system, or use near phase transition where the fluctuation is large. But on the same time, you need large enough numbers to reveal the fundamental structure, or hopefully you have several fundamental structures. But of course, we don't know. We don't know. If we knew it, we didn't have to do the simulation. So we don't know what kind of structure we get. But so this is the challenge. But you really have to be careful in choosing the system size, I think, which is fundamental. And of course, if you have a condensed matter, excluded volume effect is crucial. Recently, chemists are always also saying this. You don't, for instance, dipole moment is very small compared to this excluded volume. The effect is much larger for this. And you have to carefully incorporate experimental facts into a simple model. So, well, just for one example, this is also already published. So this is how I chose my system size at the beginning. Of course, this is just an estimation. So I think basically it's not really the lattice they are talking about. It's some kind of entity that looks like a lattice on the X-ray diffraction or other data. But they have, for instance, in taking this the alkyl chain must be, you take odd value, even value, you get some 30 or 60, 40. So you just try to make up some kind of a value that will satisfy these numbers as much as you have 480 here and 320. So this is how I chose my 1,920 molecules to do the calculation. So thank you very much. I think I'm just in time.
Questions, any comments?
So about soft matter crystals, do you have a way of predicting the space group? Because the double gyroid is the last space group, number 230. So do you have a way of predicting what we'll end up with?
No, I think, as I told you, also in the liquid crystal part, space group is not really, I mean, if you have periodic boundary conditions, you just have, you don't have a certain characteristic length that's missing. So in that sense, of course, you can mimic X-ray diffraction of these crystals. But here also, we shouldn't really rely on space groups, but use some kind of topological orbifold notation or something like to characterize them. So, well, I'm working on that with some of my collaborators, because I think many of, the soft matter literature, sometimes to me, it seems that they're misinterpreting their X-ray diffraction pattern because they are using a group theoretical analysis, which is not, as I showed you, they might not be the third characteristic length, and not the lattice in a true sense. So that is a very important point, I think. But I don't have a definite answer to that now.
Any other questions, comments?
Thank you for the interesting presentation. I'm not I come from the field of optics, but I was just wondering about the different phases. I know, like for instance, in ice, by applying some pressure or different condition, you can create some different phases or get some different phase transition. Here, you can you also apply some external force, like starting from gravity or some this kind of.
Yes, yes.
And do you expect some different phases?
Well, I haven't,
Just
I just have done these, internally balancing with the given value of the pressure. So I haven't, well, I have used some external force with a different, in a different subject, but of course, as a method, you can do it. So.
Yeah, it might seem interesting.
Any other questions? Well, if not, let's thank Dr. Aoki once again.